Hello everyone, today is the day 9th of 75 Hard Research Challenge that was started on 13th April 2024 by me, and I will be talking about what I have been reading in the last couple of days, that is direct preference optimization. Today I am going to talk about like RLHF, which was the current state of the art for training large language models on human preference data using reinforcement learning. It was developed by OpenAI and had shown great success. But recently, in NeurIPS 2023, I think, or 2024, a new algorithm called direct preference optimization was proposed, which like removes the shortcomings of RLHF. So in this video, I'm going to break this video into two parts. One will come today, one will come tomorrow, because it will otherwise be too long to digest. So I'm going to talk about RLHF and its problem today. So let's get started. Okay. So direct preference optimization, or DPO for short, tries to solve certain problems that exist in something called RLHF, which is reinforcement learning from human feedback. So both of these tasks are trying to solve the same problem, whereas DPO tries to uplift or remove the shortcomings of RLHF. So let's first understand what is the task that both of these are at the end of the day trying to solve. So let's say you have a pre-trained LLM, right, with you. So what you usually do is that you fine tune this LLM on a particular dataset. Usually these days this dataset is known of instruction tuning, right? That means this dataset has pairs where you have instructions and comma the prompt that the user may ask, followed by the response. So this is the usual dataset that people use. So once we have this dataset, we have a fine-tuned LLM, right? Fine-tuned LLM with us. Now what people have seen is that this fine-tuned LLM, while it has been like fine-tuned on this instruction dataset, it may still contain certain problems. For example, it may have certain human biases that exist in the human society, but we would like them to be removed from the large language model. For example, in this paper, these guys take a very good example that let's say you want to train a AI coding assistant, right, to understand common programming mistakes, okay, in order to correct them. So you train it on a very large data set, and let's say it is like instruction tuned now, and it shows very high quality of coding abilities, okay. Now because it has been trained on an instruction data set that has been captured from the internet, for example from Stack Overflow or something of that sort, so it might want like we want our model to be aware of common misconceptions which are believed by, let's say, more than 50% of the people, but in fact are incorrect. Because it is, our LLM would be fine tuned on a dataset based on these misconceptions. That means the dataset will already have those misconceptions. Hence, the model itself may show those misconceptions. So how do we go about having desired responses and behaviors which should ideally remove these common misconceptions, right? So for this, what we do is that we get another dataset of human preferences. In this case, what we do is that we ask a human being to label the dataset, in the sense that we have an LLM. For example, we had an LLM there. We take this LLM and we prompt it. It will give us a response. Now this response and the prompt will be shown to a human. For example, using Mechanical Turk of Amazon, and the human will score it in the range, let's say 1 to 5, then how good the response is. And maybe there may be multiple hierarchies or multiple like fine-grained scoring levels. For example, we can have a scoring for fluency, we can have a scoring for let's say efficacy or something of that sort, right? So once we have this data set, we can use this data set to further refine our fine-tuned model. Okay, so how do we go about doing this? So what people have shown is that in the case of RLHF, which is reinforcement learning from human feedback, it was developed by OpenAI. So this is a very simple 3-step process. So what they do is that they first collect the human preference data. Then using this human preference data, what does this human preference data contain? It will contain that out of two responses of from the same LLM, let's say it gives you a response y1 and a response y2, which one does the human prefer? Does the human prefer y1 or y2? This is shown here in the form of yw and yl. Okay, so that means that yw stands for winning, l stands for losing one. Okay, when you have a data set where you have an x as a instruction prompt and two preferences where yw and yl, y1 is the one preferred by humans and yl is the one not preferred by humans, we collect a data set of these preferences. Once we have this, we train a reward model, right, which in turn itself is a pre-trained fine-tuned LLM. Okay, instruction fine-tuned. Okay, once we have the reward model with us, what we will do is that we will fine-tune the LLM using this reward model. What does this reward model say and why is it called a reward model? Because in the case of reinforcement learning, that's how the nomenclature is, that every time a model gives you a correct output, you would want to give it a positive outcome, positive reward, otherwise you would want to give it a negative reward, and eventually the model will adapt its parameters to create more positive rewards and hence align itself with the preference dataset. Okay, so this is the basic formulation of RLHF. The problem with this is that because this reward model itself is a large language model and the model that you want to train itself is a large language model, and we will see that another large language model in a minute, we will see that another large language model is used and all three of them have to be kept in the GPU memory for it to train. Okay, so this is one of the problems. Second problem that RLHF faces is that of unstable training. Okay, it's very difficult to train reinforcement learning agents in general and let alone large language models of this scale, right? So because of these reasons, the authors propose direct preference optimization, which is an algorithm that implicitly optimizes the same objective as RLHF, right, but without the need of having a reward model, that is another model that tells you what is the reward for generating a particular sequence of tokens. Okay, so how do they do it? So let's first see what does RLHF do. Okay, so let's first see what are the three phases. First is supervised fine tuning, and second is the preference sampling and reward learning. Third one is the RL optimization. So in the first phase, what they do is they take a pre-trained large language model and fine tune it on a supervised data set of high quality to get something called pi SFT. Okay, second, what they do is that in the second phase they do reward modeling where they pick the pi SFT and fine tune it to predict a reward for a particular generation, right, for the particular generation against a particular prompt. Okay, so they use something called Bradley-Terry preference model, which we'll discuss in a minute, to train a reward function. The output of this model is pi reward, right. Once you have this second phase also done, in the third phase what you do is that you use this pi reward and take a copy of the pi SFT, that means the large language model which was fine tuned on a high quality data set, and you use a particular loss function that is based on the reward function that the reward model that you got in the second step, right. And this is how the three phases of the RLHF go. So I'm going to go into the details of the mathematics here a little bit. So what happens is that, let's say you generate two outputs using pi SFT given a particular prompt. Okay, so you have X as a prompt and PySFT models the probability that what should be the next word and hence a sequence of words in an autoregressive manners. And let's say you sample two outputs from this particular probability distribution, either using, let's say, top K sampling or top P sampling, which is also called nucleus sampling, or beam search, right? Let's say this y1 and y2 are there. Now let's say out of this y1 and y2, we will try to model it using Bradley-Terry preference model. In the Bradley-Terry preference model, it says that if you want to increase the preference probability of, right, the preference of y1 over y2 given x, then this is the formula that you use to model it. Okay, here simply what you are doing is taking the ratio of the reward when you preferred y1 or divided by the sum of both the values for y1 and y2, right? So essentially you are normalizing it, right? Where R denotes the reward model, whatever it is. Okay, so once you have this, what you do is that let's see that how this is used to train a particular reward model. So in this case, what you do is that now that you have this preference model with you, what you can do is that with this log likelihood, with this probability, you can define a log likelihood based loss function, which can then be used to train our PySFT that we used, that will eventually lead to Pi reward, right? So let's first see that how we reach from this particular equation to this particular equation. Let me go through it a little bit. Okay, so what do we have here? We have exponential of r star x comma y1 divided by exponential of r star x comma y1, right, plus exponential of r star x comma y2. So now let's say you want to prefer, you have a data set of the form of human preferences where given a prompt xi, you are given two outputs, the winning output and the losing output. The winning output signifies that what is the output preferred by a human over the output that was not preferred by the human. Okay, so in this equation what we will do is that we will replace y1 with yw and y2 with y losing. Okay, so we do y win y loss and we want to maximize this. Now if we can rewrite this equation in the form that 1 by 1 plus exponential r star x comma y l divided by exponential r star x comma y winning, right? Okay, so what happens here is that what we did is this, that we just simply took this particular value and moved it to the denominator, right? So now what we can do is that we can see that it is essentially saying that 1 plus exponential r star x comma y l minus r star x comma y winning, right? And then what we can see is that we do 1 plus exponential of negative r star x comma y winning minus r star x comma y loss, right? So now as you can see, this is nothing but the functional function which we are already familiar with. This is called sigmoid of r star x comma yw minus r star x comma y loss, right? So this, let's remember this, that this particular equation number 1 can be represented using sigmoid of this, right? Okay, so that's what they have done here. They have sigmoid of r winning loss and r losing loss, right? So now because we want to, this is just rewriting this equation in the form of let me just sigmoid of r star x comma y winning minus r star x comma y losing, right? So now we simply say that we want to maximize this particular probability, that is this particular equation. So we take a negative, we make a optimization function out of it, which is denoted by curly LR, which will be a function of the LLM pi reward and the data set that we have, and it will be negative log likelihood of this particular equation that we have here, right? So that's only the loss function that we have for training the reward function, right? So now that once we have trained this reward function, let's say we optimize it, we train it to our heart's content, right? Then what do? We simply use this reward model to fine tune our model further, right? How do we do that? How? So what we do is that we make a copy of pi SFT. Let's say we call it pi theta, right? It will take x as input and return y as output. Hence, it models the probability of y given x, right? Where x is our prompt or the content generated so far. So what we do is that we want this model to maximize the reward that we learned in this particular step. That is the second step. So how do we go about it? We say that okay, max over pi theta, that we want to maximize, find the maximized value, we want to maximize certain quantity where we vary the pi theta over expectation that x is coming from the dataset and y is coming from our learned policy, okay? And what do we want to maximize? We want to maximize the reward that we get for this particular prompt and the y that we generated, right? If we wanted to do it naively, we would stop here, but that's not what we are going to do, because what can happen is that if we do not have any regularization on this, then the model will get like extremely overfitted on the reward function that we have trained, which in turn was trained on the human preference data, right? So which may or may not have biases, and this particular data that we have here, on which the human preferences preferences data on which the reward function was trained, and now this particular third phase optimization is also being done, may have biases, right? But and it's because it is very small, right? So what we do, we simply say that I do not want to move far away from my reference model, right? So that means that whatever I have learned so far in my pre-training and my SFT step that was in phase 1, I do not want to move very far away from it, but I also want to maximize the reward function that I learned in the second phase. So that like makes the optimization function as r x comma y minus beta. Beta is the is a hyperparameter that controls how much you want to weigh in that the deviation should be penalized, right? So the first term is the reward reward function, and the second one is something called penalty term, KL divergence penalty term. In this case, what they are saying is that I want, because these two are like probability distributions, right? Pi theta is a probability distribution over the next word given the current past words that we have generated of seen. Similarly, pi ref is also a probability distribution. To take the difference of probability distribution, we usually use something called KL divergence. So that's what they have done, right? Okay. Now, so this is the optimization function that we have for training RLHF. This has nothing to do with DPO so far. So far, we have seen what RLHF is doing. Okay. Now that's what they have seen, that the added constraint is important as it prevents the model from deviating too far from the distribution on which the reward model is accurate, right? So now because so now we use, how do we train once we have the optimization function? How do we train on top of it? Do we use supervised learning or do we use something else? So the problem with this optimization function is that every time we are generating a sequence of words, right? We have a prompt with us, let's say prompt with us. Now using this prompt, we are generating the next word. Okay, let me use a different color here. So so we are generating the first token, then the second token, right? And then the third token. So where is this token coming from? So essentially what is happening is that as soon as you generate these, let's say you have generated 3 words, so you attend over all of these, like, and create a distribution over the next possible word in the vocabulary, right? So this particular x-axis is over the all the vocabulary, right? And y-axis shows the probability of a particular token to be generated. Now this is fine to the extent where you are training on the original reward, but what you are doing is that because you want to generate the next word, what we usually do is that we sample from this particular distribution. Okay, so because we are sampling now, we are breaking the gradient path that should have been there once we use this optimization function to back propagate, right? So for this reason, because there is no clear path to back propagate on, we use something called reinforcement learning. Okay, that's what they have said that this objective is not differentiable and is typically optimized using reinforcement learning. Okay, and they use a standard algorithm called PPO in this case. So now we have seen that there are three phases. Let me revisit. First is the SFT phase. Second is the pi reward model phase, where you learn the first is the SFT. Second one is the learning the R phi x comma y, and third one is learning the pi theta, which is the final LLM that has been trained using the human preference. Now the very first problem that we see in this is that that you have to keep all these three in the GPU memory to train this, right? Because why is that? Because here we use R phi, which was trained in second step. Here we have pi theta, which we are training currently, and here we have pi ref, which was trained in the first phase. So even when we are back propagating only on this particular parameter set, we still need these two into the GPU, and that is one of the major problems with RLHF. Right. Second problem with this is that RL in general is very difficult to train. Okay, that has I have worked in reinforcement learning, and I know this firsthand that it is very difficult to train, and unstable algorithms are there, and there are certain reasons for that. Let's not go into those in today's lecture. Okay, so now the question is, what is direct preference optimization? In the case of direct preference optimization, okay, so now because there is a problem that you are keeping all three models in the memory and RL is unstable, can we get rid of these three-step process where we first train the reward function and then using the reward function we fine tune on human preference data? Can we do something better than this? So this is what the authors of this paper are proposing. They're saying that we can get rid of all of this by consuming this reward function in the final optimization function that we want to train. Right, so there is no two-step process, there is only a single step process, and they are showing a mathematical proof that their optimization is a derivative or is based on what the optimization function of RLHF was. So now that we have seen what is the problem with RLHF, next we are going to discuss what is the solution to these problems proposed by direct preference optimization. So I'm going to stop the lecture today here only, and I'm going to restart the lecture tomorrow from here. Thank you very much, because I think this is going to be a very long lecture if we continue in a single video. Thanks.